In this video, we're going to be taking a look at how to use L'Hopital's rule with other indeterminate forms, such as 0 times infinity, infinity minus infinity, 1 to the infinity, infinity to the 0, and for some reason I wrote infinity minus infinity again. So the goal is to get it in the form of 0 over 0 or infinity over infinity. So let's take a look at our first example. The limit as x approaches infinity of 1 over x log of x. Direct substitution gives us 0 times infinity. And the trick here is we're going to move one of them. I'm just going to move 1 over x to the denominator. So we'll get log of x over 1 over x, which is just the log of x over x. And now when we pass to the limit, we get infinity over infinity, and we can use L'Hopital's rule. So using L'Hopital's rule, we can take the derivative of the top, which is 1 over x, and the derivative of the bottom, which is 1, and take the limit as we go to infinity. So we just have the limit as x goes to infinity of 1 over x, which is 0, which is the limit that we wanted to have. For our next example, let's take a look at 1 to the infinity. So we'll take a look at the limit as n approaches infinity of 1 plus a over n, all raised to the nth power. Direct substitution of this is going to give us 1 to the infinity. So we have to use a different trick here. And the trick that we're going to do is we're going to let y equal this limit, and then we're going to take the log of both sides. And we're going to use the fact that the limit of a log is the log of the limit, so we can pass the limit through the log. So taking the log of both sides, we're going to get that the log of y is equal to the limit as n approaches infinity of n log 1 plus a over n. And now passing to the limit, we get infinity times the log of 1, which is infinity times 0. And now we can use the trick that we had from example 1, and we'll just move that n to the denominator. So we'll get the limit as n approaches infinity of the log of 1 plus a over n over 1 over n. And now we have something of the form 0 over 0, so we can use L'Hopital's rule. Now, taking the derivative of the top, we get 1 over 1 plus a over n times the derivative of 1 plus a over n, all divided by the derivative of 1 over n, which is going to be negative 1 over n squared. Now, by taking the derivative of a over n, we get negative a over n squared. So in total, on the top, we have 1 over 1 plus a over n times negative a over n squared over negative 1 over n squared. So we can factor out that a, and we'll get positive a over 1 plus a over n times negative 1 over n squared over negative 1 over n squared. And we see a common factor in the numerator and denominator, so we can just cancel those out. And in doing so, we get the limit as n approaches infinity of a over 1 plus a over n. Now taking that limit, we get a over 1 plus 0, which is just a. But remember that that's the log of the function that we wanted to take the limit of. So y, which is equal to the initial limit, is going to be equal to e to the a. Now, all the other limits that are of the form 1 to the infinity, 0 to the 0, can all be solved using this trick. So we're next going to move on to an infinity minus infinity example. And for this, we're going to look at the limit as x approaches 0 from the right of 1 over x plus log of x. And that gives us infinity plus negative infinity, which is infinity minus infinity, one of our indeterminate forms. So we're going to use a similar trick here. We're going to let y equal the limit, and we're going to take the log of both sides. So in doing so, we get the log of y is equal to the limit as x approaches 0 from the right of the log of the quantity, so the whole thing, 1 over x plus log of x. Now remember the property that if I have the log of a sum, I can break that up into the product of the logs. So we're going to get the limit of the log of 1 over x plus the log of x, or times the log of x. Now, we can break down 1 over x inside the log, and we can just make that negative log of x. So let's just do that real quick to simplify our derivatives when we eventually have to take them. So direct substitution here is going to give us negative infinity for the limit as we approach 0 from the right of negative log of x. And then we have the log of x as we approach 0 from the right. So it's going to be another infinity. And we have infinity times infinity, which is infinity. And we went from an indeterminate form to an infinite limit, which is okay. That just happens sometimes. Thank you for watching. I hope this helps.